In the farthest reaches of the universe, beyond the familiar stars and galaxies we see in the night sky, there exist objects so powerful that they outshine entire galaxies. These objects are known as quasars, the brightest and most energetic phenomena ever discovered in the cosmos. A single quasar can release more energy than hundreds of billions of stars combined. From billions of light years away, they appear as tiny points of light in telescopes, yet the power they produce is almost unimaginable. For decades, astronomers were puzzled by these mysterious signals coming from deep space. At first, no one understood what could possibly generate such enormous amounts of energy. These objects were so bright and distant that they seemed to defy everything scientists knew about the universe. The answer, when it finally emerged, was even more astonishing. At the center of every quasar lies a supermassive black hole, millions or even billions of times more massive than the Sun. As gas, dust, and entire stars fall toward the black hole, they form a blazing disk of superheated material spiraling inward at incredible speeds. This swirling disk becomes so hot and luminous that it shines across billions of light years of space. In fact, some quasars are so bright that we can still see them today, even though their light began its journey when the universe was still very young. These cosmic beacons allow astronomers to look back in time, revealing what the universe looked like billions of years ago. But quasars are more than just distant lights in the darkness. They are among the most extreme and violent environments in existence, places where gravity, energy, and radiation reach levels far beyond anything found in our own galaxy. In this documentary, we will explore how quasars form, why they shine so brilliantly, and what these extraordinary objects can teach us about the evolution of galaxies and the early universe itself. Long before astronomers understood what quasars were, the night sky appeared calm and predictable. Stars slowly moved across the heavens, planets followed their familiar paths, and distant galaxies formed faint spirals of light through powerful telescopes. Yet hidden among these distant points of light were objects so powerful and mysterious that they would eventually change our understanding of the universe. The story of quasars begins in the middle of the 20th century, during a time when radio astronomy was rapidly transforming the way scientists explored space. Traditional telescopes observed the universe using visible light, but radio telescopes detect radio waves emitted by celestial objects. These waves can reveal phenomena invisible to ordinary optical instruments. In the 1950s, astronomers using radio telescopes began detecting strong radio signals coming from certain regions of the sky. These signals were far more intense than those produced by typical stars. At first, scientists assumed they were coming from distant galaxies. But when astronomers tried to identify the visible objects responsible for these radio emissions, they encountered a puzzling problem. The sources appeared to look like stars. Through optical telescopes, the objects seemed small and point-like, much like ordinary stars within our own galaxy. Yet the radio signals they produced were far too powerful to be generated by any known type of star. The mystery deepened as more of these radio sources were discovered. One of the most important breakthroughs came in 1963, when astronomer Martin Schmidt studied a radio source known as 3C273. Using spectroscopic analysis, Schmidt examined the light emitted by the object and noticed something extraordinary. The spectral lines did not match any known elements at their expected wavelengths. At first, the data seemed confusing, but Schmidt realized that the lines were actually familiar patterns that had been dramatically shifted toward the red end of the spectrum. This phenomenon is known as redshift. Redshift occurs when light from an object is stretched as the object moves away from the observer. In the expanding universe, distant galaxies move away from us, causing their light to shift toward longer wavelengths. When Schmidt calculated the redshift of 3C273, the result was astonishing. The object was not a nearby star at all. It was located billions of light-years away. If this distant object appeared as bright as a star in Earth's sky, it meant that it must be producing an enormous amount of energy. In fact, it was emitting more light than an entire galaxy containing hundreds of billions of stars. This discovery revealed the existence of a completely new class of cosmic objects. They became known as quasi-stellar objects, a name chosen because they looked like stars but were clearly something very different. Over time, the term was shortened to quasars. Once astronomers began searching for them, they discovered that quasars were scattered throughout the universe. Some were extremely distant, meaning their light had traveled billions of years before reaching Earth. Observing these objects allowed scientists to look far back in time, into an era when the universe was much younger than it is today. But the question remained: what could possibly produce such extraordinary brightness? For many years, the answer remained uncertain. Some early theories suggested that quasars might be unusual types of stars undergoing violent explosions. Others proposed that they might be entire galaxies experiencing intense bursts of star formation. However, none of these explanations could fully account for the immense energy produced by quasars. The breakthrough came when astronomers began studying the centers of galaxies. By the 1970s and 1980s, growing evidence suggested that many galaxies contain supermassive black holes at their cores. These black holes are millions or even billions of times more massive than the Sun. Unlike stellar black holes formed from collapsing stars, supermassive black holes appear to have formed during the earliest stages of galaxy formation. When matter falls toward a black hole, it does not simply disappear instantly. Instead, gas and dust spiral inward, forming a rotating structure known as an accretion disk. Within this disk, matter moves at incredible speeds as it falls deeper into the black hole's gravitational well. Friction between particles in the disk causes the gas to heat to extremely high temperatures. As the material becomes hotter, it begins to glow with intense radiation across many wavelengths, including visible light, ultraviolet light, and X-rays. The energy released in this process is enormous. In fact, the conversion of gravitational energy into radiation in an accretion disk can be far more efficient than nuclear fusion inside stars. A small amount of matter falling into a supermassive black hole can produce more energy than millions of stars. When this process occurs on a large scale in the center of a galaxy, the result is a quasar. The black hole itself remains invisible, but the glowing accretion disk surrounding it shines with extraordinary brightness. From vast distances across the universe, the disk appears as a brilliant point of light. In addition to the accretion disk, many quasars produce powerful jets of energy that shoot outward from the regions near the black hole. These jets consist of highly energetic particles, accelerated to speeds approaching the speed of light. Magnetic fields around the black hole help channel this material into narrow beams that extend far beyond the host galaxy. Some of these jets stretch for millions of light-years through intergalactic space. The presence of these jets further contributes to the incredible luminosity of quasars. But another remarkable aspect of quasars is when they appeared in the history of the universe. Observations show that quasars were far more common billions of years ago than they are today. This suggests that the early universe contained many actively feeding supermassive black holes. During the first few billion years after the Big Bang, galaxies were still forming and evolving. Large amounts of gas and dust were available to fall into the central black holes of these galaxies. As this material accumulated, it powered intense quasar activity. Over time, however, much of the available gas within galaxies became locked into stars. As the supply of material feeding the black holes decreased, quasar activity gradually declined. Today, most supermassive black holes in nearby galaxies are relatively quiet. Even the black hole at the center of our own galaxy, known as Sagittarius A star, is currently inactive, compared with the brilliant quasars observed in the distant universe. Yet the study of quasars continues to reveal valuable information about the cosmos. Because they are so bright, quasars can be observed across enormous distances. Their light travels through vast regions of intergalactic space before reaching Earth. Along the way, the light interacts with clouds of gas located between galaxies. By analyzing how the quasar's light is absorbed by these clouds, astronomers can learn about the composition and distribution of matter throughout the universe. In this way, quasars serve as powerful cosmic beacons that illuminate the structure of the universe itself. They allow scientists to study regions of space that would otherwise remain invisible. Even today, more than 60 years after their discovery, quasars remain among the most fascinating objects known to astronomy. They represent some of the most extreme environments in existence, places where gravity, energy, and radiation reach levels far beyond anything found within our own galaxy. And as telescopes continue to improve, astronomers are discovering quasars located even farther away than ever before. Some of these distant quasars formed when the universe was less than 1 billion years old. Their existence raises profound questions about how supermassive black holes formed so quickly after the birth of the universe. Understanding quasars is therefore not only about studying extreme cosmic objects, it is also about uncovering the story of how galaxies, black holes, and the universe itself evolved over billions of years. And as scientists continue exploring these brilliant beacons of deep space, quasars remain one of the most powerful reminders of just how extraordinary the universe truly is. When astronomers finally realized that quasars were located billions of light-years away, a new and even deeper mystery appeared. If these objects were so distant yet still visible through telescopes as bright points of light, they must be producing unimaginable amounts of energy. The question that immediately followed was simple but profound. What kind of engine could power something so bright? For years, scientists struggled to find an explanation. At first, many researchers believed quasars might be massive explosions or unusual clusters of stars. But when astronomers began calculating the energy output of these objects, those ideas quickly collapsed. A single quasar could emit thousands of times more energy than an entire galaxy like the Milky Way. No known type of star or stellar explosion could produce that level of power. Eventually, scientists began considering a much more extreme possibility. The source of this incredible energy might be supermassive black holes. Black holes were already known to exist as the remnants of collapsed stars, but those stellar black holes usually contain only a few times the mass of the Sun. The objects needed to power quasars would have to be vastly larger, millions or even billions of times more massive than our Sun. Such black holes would be located at the centers of galaxies. Over time, astronomers began gathering evidence supporting this idea. Observations showed that many galaxies contained compact, extremely massive objects at their cores. These objects exerted powerful gravitational forces on nearby stars, causing them to orbit at incredible speeds. The most logical explanation for these observations was the presence of supermassive black holes. If gas, dust, and even entire stars fell toward these black holes, enormous amounts of gravitational energy could be released. But the process of falling into a black hole is far from simple. Matter does not plunge directly into the event horizon. Instead, it begins to spiral inward, forming a rotating structure called an accretion disk. This disk plays a crucial role in creating the brilliance of quasars. Within the accretion disk, enormous amounts of gas move at tremendous speeds. As the gas particles collide and rub against one another, friction heats the material to extreme temperatures. In the inner regions of the disk, temperatures can reach millions of degrees. At such temperatures, the gas glows intensely. Radiation pours out across the electromagnetic spectrum, from visible light to ultraviolet radiation and powerful X-rays. This glowing disk becomes one of the brightest structures in the universe. Although the black hole itself remains completely dark, the material surrounding it shines with astonishing brightness. The amount of energy produced by this process is extraordinary. When matter falls toward a black hole, a portion of its mass is converted directly into energy. According to Einstein's famous equation E equals mc squared, even a small amount of mass can generate enormous energy. In fact, accretion disks around black holes can convert matter into energy far more efficiently than nuclear fusion inside stars. While stars convert only a small percentage of their mass into energy, accretion disks can convert up to 10% of the falling material into radiation. This efficiency explains why quasars can outshine entire galaxies. Another remarkable feature of quasars is the presence of relativistic jets. Near the center of the accretion disk, powerful magnetic fields twist and interact with the rapidly rotating gas. These magnetic forces can channel particles away from the black hole along narrow beams. The result is a pair of jets shooting outward from opposite sides of the disk. These jets travel at speeds extremely close to the speed of light. They can extend for hundreds of thousands or even millions of light years, sometimes reaching far beyond the galaxy that hosts the quasar. As the jets move through space, they interact with surrounding gas and magnetic fields, producing intense radio waves. This is why many quasars were first detected by radio telescopes before their optical nature was understood. The presence of these jets reveals how violent the environment near a quasar can be. Close to the black hole, gravity becomes so strong that space and time themselves are distorted. Matter spiraling into the accretion disk reaches velocities approaching a significant fraction of the speed of light. Radiation from the disk becomes so intense that it can push surrounding material outward, creating powerful winds that sweep across the host galaxy. In some cases, these winds may even influence the evolution of the galaxy itself. Astronomers now believe that supermassive black holes and their host galaxies grow together over time. As galaxies accumulate gas and form stars, some of that gas eventually falls toward the central black hole. When the black hole becomes active and forms a quasar, the radiation and jets it produces can heat or expel gas from the galaxy. This process may regulate how quickly new stars form. In this way, quasars may play a crucial role in shaping the development of galaxies throughout cosmic history. Another fascinating aspect of quasars is their incredible distance from Earth. Many quasars are located so far away that their light has taken billions of years to reach us. When astronomers observe these objects, they are effectively looking back in time. Some of the most distant quasars known today formed when the universe was less than 1 billion years old. This raises an important question. How did such massive black holes form so early in cosmic history? Creating a black hole containing billions of solar masses requires enormous amounts of matter. Yet, in the early universe, galaxies themselves were still forming. Scientists are still trying to understand how these supermassive black holes grew so quickly. One possibility is that the first generation of stars in the universe, known as population 3 stars, were far more massive than most stars today. When these enormous stars collapsed, they may have formed large black holes that later grew by swallowing surrounding gas. Another theory suggests that massive clouds of gas in the early universe collapsed directly into black holes without forming stars first. These direct collapse black holes could have started with masses already thousands of times greater than the Sun. Over time, these early black holes may have grown rapidly through accretion and mergers with other black holes. Understanding this process remains one of the biggest challenges in modern astrophysics. Quasars provide valuable clues because their brightness allows astronomers to detect them even at extreme distances. Each newly discovered quasar helps scientists understand how galaxies and black holes evolved during the earliest epochs of the universe. Modern telescopes have dramatically expanded our ability to study these objects. Observatories such as the Hubble Space Telescope and the James Webb Space Telescope are capable of detecting extremely distant quasars that formed shortly after the Big Bang. The James Webb Telescope, in particular, is designed to observe infrared light from the earliest galaxies and black holes. Using these instruments, astronomers have begun discovering quasars that existed when the universe was only 600 to 700 million years old. These discoveries suggest that supermassive black holes formed much earlier than scientists once believed. The study of quasars continues to push the limits of our understanding of the cosmos. They represent some of the most extreme environments ever observed. places where gravity, radiation, and energy interact on unimaginable scales. From their blazing accretion disks to their enormous jets stretching across intergalactic space, quasars reveal how powerful black holes can become when surrounded by vast reservoirs of matter. And as astronomers continue searching deeper into the universe, they are discovering that these brilliant cosmic beacons may hold the key to understanding the earliest chapters of cosmic history. As astronomers continued studying quasars, one surprising pattern began to emerge. These incredibly bright objects were not evenly distributed throughout the universe. Instead, they appeared much more frequently in the distant universe than in the nearby one. This observation revealed something remarkable about cosmic history. When scientists look at extremely distant quasars, they are seeing light that left those objects billions of years ago. Because light takes time to travel through space, observing distant objects is essentially looking back in time. What astronomers discovered was that quasars were far more common when the universe was young. Roughly 10 to 12 billion years ago, the universe was filled with active quasars. Many galaxies contained supermassive black holes that were rapidly feeding on large amounts of gas and dust. Today, however, quasars are relatively rare. Most galaxies in the modern universe contain supermassive black holes that are quiet and inactive. These black holes still exist, but they are no longer surrounded by the enormous accretion disks that once powered quasar activity. Understanding this change is an important part of understanding how galaxies evolve. In the early universe, galaxies were still forming and growing. Huge clouds of gas flowed through space, gradually collapsing under gravity to form stars and galaxies. These gas reservoirs also provided abundant fuel for supermassive black holes at the centers of galaxies. As matter spiraled into the black hole, the accretion disk grew hotter and brighter, creating the intense radiation that defines a quasar. During this period, some galaxies hosted quasars so luminous that they could outshine every star in the galaxy combined. But this phase did not last forever. Over time, galaxies consumed much of their available gas to form stars. As the supply of gas decreased, less material was available to feed the central black holes. Without a steady flow of matter falling into the accretion disk, the quasar gradually faded. Eventually, the black hole entered a quiet phase. Today, many galaxies still contain supermassive black holes, but most of them are dormant. Even the black hole at the center of our own galaxy, known as Sagittarius A star, is currently inactive, compared with the blazing quasars observed in distant galaxies. Although Sagittarius A star contains about 4 million times the mass of the Sun, it emits relatively little radiation because it is not actively consuming large amounts of material. However, astronomers believe that the Milky Way's central black hole may have been much more active in the distant past. Evidence suggests that powerful eruptions may have occurred millions of years ago, producing enormous structures known as the Fermi bubbles, giant lobes of gamma-ray radiation extending above and below the plane of our galaxy. These structures may represent the remnants of past activity from the Milky Way's central black hole. If this interpretation is correct, it means our galaxy may once have hosted a quasar-like phase long ago. Another fascinating discovery about quasars is that they are often found in massive galaxies undergoing intense interactions. In many cases, quasar activity appears to be triggered when galaxies collide or merge with one another. When two galaxies approach each other, their gravitational forces can disrupt the motion of gas within both systems. Huge clouds of gas may be driven toward the central regions of the galaxies. This sudden influx of material provides fuel for the supermassive black holes at the centers. As the black hole begins to consume the incoming gas, the accretion disk forms and rapidly heats up. The result is a brilliant quasar that can shine across vast distances. Galaxy mergers are therefore believed to be one of the primary triggers for quasar activity. This connection between quasars and galaxy evolution has become an important focus of modern astrophysics. Researchers now believe that supermassive black holes and their host galaxies grow together over cosmic time. As galaxies accumulate mass through mergers and star formation, their central black holes also grow by consuming gas and occasionally merging with other black holes. Observations have revealed a surprising relationship between the mass of a galaxy's central black hole and the size of the galaxy's central bulge of stars. This relationship suggests that the growth of black holes and galaxies is closely linked. Quasars may play an important role in this process. When a quasar becomes extremely bright, the radiation and powerful winds produced by the accretion disk can push gas away from the galaxy's center. This process is known as quasar feedback. Quasar feedback may regulate the formation of new stars by heating or expelling gas that would otherwise collapse into new stellar systems. In some cases, quasar-driven winds can travel thousands of light years across the host galaxy. These winds can carry enormous amounts of energy, reshaping the galaxy's structure over time. Some astronomers believe that quasar feedback helps explain why many massive galaxies eventually stop forming new stars. By removing gas from the central regions, quasars may effectively shut down further star formation. This idea highlights how black holes, once thought to be simple gravitational sinks, can actually influence entire galaxies. Another remarkable feature of quasars is the variability of their brightness. Unlike galaxies, which maintain relatively steady luminosity over long periods of time, quasars can change in brightness on timescales ranging from days to years. These variations occur because the material within the accretion disk is constantly shifting and interacting. Gas clouds falling toward the black hole may collide, compress, or heat up, causing fluctuations in the amount of radiation emitted. By studying these brightness variations, astronomers can estimate the size of the quasar's central region. Surprisingly, the region producing most of the light is extremely small compared with the size of a galaxy. Despite emitting enormous energy, the bright core of a quasar may be only a few light days across. This compact size further supports the idea that the energy source must be a supermassive black hole surrounded by a dense accretion disk. Quasars are also important tools for studying the structure of the universe itself. Because they are so bright, they can be observed across enormous distances. Their light travels through vast regions of space before reaching Earth. Along the way, the light passes through clouds of gas located between galaxies. These clouds absorb specific wavelengths of light, leaving characteristic patterns in the quasar's spectrum. By analyzing these absorption patterns, astronomers can map the distribution of matter throughout the universe. This technique has helped scientists study the intergalactic medium, the diffuse gas that fills the space between galaxies. In many ways, quasars act like cosmic flashlights, illuminating the otherwise invisible structures of the universe. Through their light, astronomers can trace the evolution of matter across billions of years of cosmic history. The study of quasars, therefore, connects several major fields of astronomy, from black hole physics to galaxy evolution and the large-scale structure of the universe. Each new quasar discovered provides another piece of the puzzle, helping scientists understand how the universe grew and changed over time. Even after decades of research, these extraordinary objects continue to reveal new mysteries. They remain among the most powerful and distant beacons ever observed in the cosmos, reminders that the universe still holds phenomena far beyond anything we experience in our own corner of space. As astronomers continued studying quasars in greater detail, they began to realize that these objects are not only incredibly bright, but also extraordinarily complex. A quasar is not a single, simple structure. Instead, it is a powerful system composed of several different components working together around a supermassive black hole. At the center of every quasar lies the black hole itself. This black hole may contain millions, hundreds of millions, or even billions of times the mass of the Sun. Its gravity dominates the surrounding region of space, pulling nearby gas, dust, and sometimes even entire stars toward it. Yet the black hole itself remains invisible. The intense brightness of a quasar does not come from the black hole directly, but from the matter that surrounds it. The most important structure in this system is the accretion disk. As gas falls toward the black hole, it begins to rotate faster and faster due to the conservation of angular momentum. Instead of plunging straight inward, the gas forms a flattened disk orbiting the black hole. Within this disk, the gas particles move at incredible speeds, often a significant fraction of the speed of light. These particles collide constantly, generating enormous friction. The friction heats the gas to extremely high temperatures, causing it to glow with intense radiation. The inner regions of the disk can reach temperatures of millions of degrees, producing powerful ultraviolet light and X-rays. This glowing disk is the main source of a quasar's extraordinary brightness. Even though the disk itself may be only a few light days across, it can emit more energy than an entire galaxy. Surrounding the accretion disk is another important structure known as the broad line region. This region consists of clouds of gas moving at extremely high velocities around the black hole. Because these clouds orbit so close to the intense gravitational field, they can travel at thousands of kilometers per second. When radiation from the accretion disk passes through these gas clouds, the atoms within the clouds absorb and re-emit light at specific wavelengths. This produces the broad emission lines seen in the spectra of quasars. The extreme speeds of the gas clouds cause these spectral lines to become widened or broadened due to the Doppler effect. By measuring the width of these lines, astronomers can estimate how fast the gas is moving. From these velocities, scientists can calculate the mass of the black hole powering the quasar. Beyond the broad line region lies another structure known as the dusty torus. The torus is a thick ring of gas and dust that surrounds the central region of the quasar. It forms when radiation and winds from the accretion disk push material outward from the inner regions. This dusty structure can obscure the central engine of the quasar from certain viewing angles. If the torus blocks our direct view of the accretion disk, the quasar may appear less bright or exhibit different spectral features. In fact, many objects known as active galactic nuclei are thought to be quasars viewed from different angles. This idea forms the basis of the unified model of active galaxies. According to this model, quasars, radio galaxies, and several other types of energetic galactic cores may all be powered by the same basic mechanism: a supermassive black hole surrounded by an accretion disk. The differences we observe arise mainly from the orientation of the system relative to Earth. Another dramatic feature of many quasars is the presence of enormous relativistic jets. These jets emerge from the regions close to the black hole and shoot outward in opposite directions along the rotation axis of the accretion disk. The particles within these jets travel at speeds approaching the speed of light. Although the exact mechanism that launches these jets is still being studied, magnetic fields appear to play a crucial role. As the accretion disk rotates, it twists and amplifies magnetic field lines near the black hole. These fields can accelerate charged particles away from the disk and channel them into narrow beams extending far into space. Some quasar jets stretch for millions of light-years, far beyond the host galaxy. As the jets move through intergalactic space, they interact with surrounding gas and magnetic fields, producing powerful radio waves. This is why many quasars were first discovered using radio telescopes. In certain cases, the jets point almost directly toward Earth. When this happens, the radiation from the jet appears even brighter due to a phenomenon known as relativistic beaming. Objects observed in this orientation are often classified as blazars, a particularly energetic type of active galaxy. Studying these jets provides valuable insights into how energy is transported across enormous distances in the universe. But the influence of quasars does not stop at the scale of their host galaxies. The energy released by a quasar can affect the surrounding intergalactic environment as well. Powerful winds generated by the accretion disk can push gas outward from the center of the galaxy at speeds of thousands of kilometers per second. These winds may carry enormous quantities of material away from the galaxy's core. In some cases, quasar winds are powerful enough to remove large amounts of gas from the host galaxy entirely. This process can slow or even halt the formation of new stars. Astronomers believe this mechanism, known as quasar feedback, may play a key role in regulating the growth of galaxies. Without such feedback, galaxies might continue forming stars indefinitely. Instead, quasar activity may periodically heat or expel gas, limiting the rate at which new stars can form. This interaction between supermassive black holes and their host galaxies represents one of the most important discoveries in modern astrophysics. It suggests that the evolution of galaxies is closely connected to the behavior of the black holes at their centers. Another fascinating property of quasars is their incredible variability. Because the accretion disk is constantly changing as new material falls inward, the brightness of a quasar can fluctuate over time. Some quasars vary in brightness over months or years, while others show more rapid changes. These variations provide valuable clues about the size and structure of the central engine. Since light cannot travel faster than a certain speed, any changes in brightness must originate from a region no larger than the distance light can travel during the observed time interval. By studying these fluctuations, astronomers have confirmed that the energy source of quasars must be extremely compact, consistent with the size of a supermassive black hole's accretion disk. Despite decades of research, quasars continue to challenge scientists with new questions. How did supermassive black holes grow so rapidly in the early universe? What determines when a galaxy becomes an active quasar? How exactly are the enormous jets launched from the regions near black holes? These questions remain at the forefront of modern astrophysics. With the development of powerful new observatories, astronomers are now able to study quasars in greater detail than ever before. Telescopes such as the James Webb Space Telescope, the Atacama Large Millimeter Array, and the Event Horizon Telescope are helping scientists explore the environments surrounding supermassive black holes. These instruments allow researchers to examine the structure of accretion disks, trace the motion of gas clouds near black holes, and even image the shadows of black holes themselves. Each new discovery brings us closer to understanding how quasars operate and how they have shaped the evolution of the universe. Quasars are not merely distant points of light. They are among the most powerful engines in the cosmos, cosmic beacons powered by gravity, matter, and energy on unimaginable scales. And as astronomers continue exploring the deep universe, these brilliant objects will remain essential clues to the story of how galaxies, black holes, and the universe itself came to be. While quasars are among the brightest objects ever discovered in the universe, one of their most fascinating aspects is how they allow astronomers to study the cosmos across unimaginable distances and timescales. Because they shine with such extraordinary brightness, quasars can be observed even when they are located billions of light-years away. In many cases, the light we see from a quasar today began its journey long before the Earth even existed. This makes quasars some of the most powerful tools astronomers have for exploring the early universe. When a telescope observes a quasar that is 10 billion light-years away, it is essentially seeing the universe as it looked 10 billion years ago. The light from that object left the quasar when galaxies were still forming, and the cosmos was far younger than it is today. In this way, quasars act like cosmic time machines. By studying them, astronomers can observe conditions that existed during the early stages of cosmic evolution. One of the most valuable things scientists learn from quasars comes from analyzing their spectra, the detailed patterns of light produced by the objects. When light from a quasar travels across the universe, it passes through enormous regions of space filled with extremely thin clouds of gas. Although these clouds are almost invisible, they leave subtle fingerprints on the light that travels through them. Atoms within the gas absorb specific wavelengths of light, producing narrow dark lines in the quasar's spectrum. These absorption lines reveal the presence of elements such as hydrogen, helium, and heavier atoms scattered throughout intergalactic space. By studying these lines, astronomers can map the distribution of matter between galaxies. This technique has led to the discovery of a structure known as the cosmic web. The cosmic web is a vast network of gas and dark matter that stretches across the universe. Galaxies are not distributed randomly through space. Instead, they form along enormous filaments of matter that connect clusters of galaxies together. Between these filaments lie huge empty regions known as cosmic voids. Quasar light passing through this web allows scientists to detect these otherwise invisible structures. In effect, quasars illuminate the universe in the same way that a distant lighthouse might reveal fog or clouds in the darkness. Without quasars, it would be far more difficult to study the thin gas that fills the space between galaxies. Another important discovery involving quasars is related to the ionization era of the universe. In the earliest period after the Big Bang, the universe was filled with hot plasma. As the universe expanded and cooled, protons and electrons combined to form neutral hydrogen atoms. This period, known as recombination, occurred about 380,000 years after the Big Bang. For millions of years afterward, the universe was filled mostly with neutral hydrogen gas. During this time, the cosmos was relatively dark because neutral hydrogen absorbs much of the ultraviolet light produced by early stars. But eventually, something changed. The first stars and galaxies began producing enormous amounts of ultraviolet radiation. This radiation ionized the hydrogen gas, stripping electrons away from atoms and transforming the intergalactic medium into a transparent plasma once again. This transformation is known as the epoch of rionization. Quasars play a key role in helping astronomers understand when and how this event occurred. Because some quasars formed very early in cosmic history, their light travels through gas that existed before and during this transition. By studying how the quasar's light is absorbed by hydrogen clouds along the way, scientists can determine how much of the universe had become ionized at different points in time. These observations provide valuable clues about the first stars and galaxies. Quasars are also essential for studying dark matter, one of the most mysterious components of the universe. Dark matter does not emit or absorb light, making it impossible to observe directly with telescopes. However, its gravitational influence shapes the distribution of galaxies and gas throughout the cosmos. When light from a distant quasar passes near massive objects, such as galaxies or clusters of galaxies, gravity can bend the path of the light. This effect is known as gravitational lensing. In some cases, the gravity of a foreground galaxy can split the light from a single quasar into multiple images. Astronomers observing these systems may see 2, 4, or even more separate points of light that all originate from the same distant quasar. By studying these gravitational lens systems, scientists can measure the distribution of mass in the lensing galaxy, including its dark matter. Gravitational lensing, therefore, provides one of the most powerful tools for studying the invisible mass that dominates much of the universe. Quasars also help astronomers measure the expansion of the universe, because their distances can be estimated through redshift measurements. Quasars provide important data points for understanding how fast the universe has expanded over time. some researchers are exploring ways to use quasars as standard candles, objects with known luminosities that can be used to measure cosmic distances. If this technique can be refined, quasars could help astronomers map the expansion history of the universe with even greater precision. Despite their usefulness as cosmic probes, quasars remain deeply mysterious in many ways. One major puzzle concerns how supermassive black holes managed to grow so quickly in the early universe. Observations have revealed quasars powered by black holes containing billions of solar masses when the universe was less than 1 billion years old. Growing such enormous black holes in such a short time is difficult to explain using standard models of black hole growth. Some scientists believe that early black holes may have formed from the collapse of extremely massive gas clouds. Others suggest that frequent mergers between smaller black holes may have accelerated their growth. Understanding how these early black holes formed is one of the most important challenges in modern astrophysics. New observations from advanced telescopes are beginning to shed light on this mystery. The James Webb Space Telescope, launched in 2021, is capable of observing extremely distant galaxies and quasars that formed during the earliest epochs of the universe. Using Webb's powerful infrared instruments, astronomers have already discovered several quasars that existed when the universe was only a few 100 million years old. These discoveries are forcing scientists to rethink their models of early cosmic evolution. As researchers continue studying these objects, quasars may reveal how the first black holes formed and how they shaped the growth of galaxies across billions of years. Even today, the brightest quasars can still be seen from across immense cosmic distances. They remain some of the most powerful beacons in the universe, shining across billions of light years and illuminating the structure of the cosmos itself. Through their light, astronomers can explore the earliest chapters of cosmic history, map the invisible web of matter-connecting galaxies, and study the extreme physics surrounding supermassive black holes. In many ways, quasars are not only the brightest objects in the universe, they are also among the most important windows into the story of how the universe came to be. Despite decades of research and observation, quasars remain among the most mysterious objects in the universe. Scientists have learned a great deal about how they work, yet many fundamental questions still remain unanswered. One of the biggest mysteries is how the supermassive black holes that power quasars formed so quickly in the early universe. Observations have revealed quasars that existed when the universe was less than 1 billion years old. Some of these quasars are powered by black holes containing billions of times the mass of the Sun. For astronomers, this discovery raises a profound challenge. Under normal circumstances, black holes grow slowly. A black hole increases its mass by pulling in surrounding matter through accretion. But this process has natural limits. As material falls toward the black hole and forms an accretion disk, the disk produces enormous amounts of radiation. That radiation pushes outward against incoming gas, slowing down the rate at which matter can continue falling inward. This balance between gravity pulling material in and radiation pushing it away is known as the Eddington limit. Because of this limit, black holes cannot grow arbitrarily fast. Even under ideal conditions, building a black hole containing billions of solar masses should take billions of years. Yet the early quasars we observe appear to have reached enormous masses in a fraction of that time. This problem has led astronomers to explore several possible explanations. One idea suggests that the first generation of stars in the universe may have been far larger than stars that form today. These ancient stars, known as population 3 stars, formed from primordial gas composed almost entirely of hydrogen and helium. Without heavier elements to cool the gas clouds, these early stars may have grown extremely massive, possibly hundreds of times the mass of the Sun. When such massive stars reached the end of their lives, they would have collapsed into large black holes. These early black holes could then serve as seeds for the supermassive black holes that later powered quasars. But even with massive stellar seeds, reaching billions of solar masses so quickly remains difficult. Another possibility involves the direct collapse of enormous gas clouds. Instead of forming stars first, some extremely massive gas clouds in the early universe may have collapsed directly into black holes. If a cloud containing hundreds of thousands of solar masses collapsed under gravity without fragmenting into stars, it could form a large black hole almost immediately. These objects are known as direct collapse black holes. Starting with such large seeds would make it easier for black holes to grow into the giants observed in early quasars. There is also evidence that black holes can grow rapidly through mergers. In the early universe, galaxies frequently collided and merged with one another. When two galaxies merge, their central black holes may eventually spiral together and combine into a single, larger black hole. Repeated mergers could help explain how supermassive black holes gained mass so quickly. Understanding these processes is one of the main goals of modern observational astronomy. New instruments are allowing scientists to search deeper into the universe than ever before. One of the most powerful tools for studying distant quasars is the James Webb Space Telescope. Unlike earlier telescopes, Webb is designed to observe infrared light from extremely distant objects whose light has been stretched by cosmic expansion. Using this capability, astronomers can detect quasars that formed during the earliest epochs of galaxy formation. The first results from Webb have already revealed galaxies and black holes that appear far earlier than many theoretical models predicted. These discoveries are forcing scientists to reconsider how quickly cosmic structures formed after the Big Bang. Another key area of quasar research involves the physics of accretion disks. Although scientists understand the general concept of matter spiraling into black holes, the detailed behavior of accretion disks is incredibly complex. Gas within the disk is affected by gravity, magnetic fields, radiation pressure, and turbulence. The interaction between these forces determines how efficiently matter flows inward and how much energy is released in the process. One important process occurring within accretion disks is known as magnetorotational instability. This instability arises when magnetic fields interact with rotating gas in the disk. The result is turbulence that helps transport angular momentum outward, allowing gas to gradually move inward toward the black hole. Without this mechanism, the gas would remain trapped in stable orbits and would not fall into the black hole efficiently. Despite progress in computer simulations many aspects of accretion disk physics remain difficult to model. Another major puzzle concerns the origin of quasar jets. These jets are among the most powerful phenomena in the universe, capable of carrying enormous amounts of energy across vast cosmic distances. Observations show that the jets originate from regions extremely close to the black hole, sometimes within a few times the radius of the event horizon. Magnetic fields are believed to play a critical role in launching and accelerating these jets. One leading explanation is the Blandford-Znajek process. According to this theory, energy can be extracted directly from the rotation of a spinning black hole through magnetic fields anchored in the surrounding accretion disk. As the black hole spins, it twists the magnetic field lines around it. These fields can then channel energy outward, launching particles at relativistic speeds along the rotational axis. If this mechanism is correct, it means that black holes are not only gravitational sinks, but also powerful engines capable of releasing enormous amounts of energy. The study of quasar jets has also helped astronomers understand how energy travels across intergalactic space. When these jets collide with surrounding gas, they create shock waves and enormous lobes of radio emission. These structures can extend hundreds of thousands or even millions of light-years away from the quasar. In some cases, the jets may even influence neighboring galaxies by heating the gas in galaxy clusters and preventing it from cooling and forming stars. Thus, the effects of quasars may extend far beyond the galaxies that host them. Another area of active research involves the variability of quasars. Astronomers have observed that many quasars fluctuate in brightness over time. Some changes occur over periods of months or years, while others can happen more rapidly. These variations provide clues about the structure of the accretion disk and the processes occurring near the black hole. Because the central region of a quasar is so compact, even small changes in the flow of gas can lead to noticeable changes in brightness. By monitoring these fluctuations, astronomers can learn about the size and dynamics of the regions closest to the black hole. In recent years, new techniques have even allowed scientists to observe echoes of light within quasar systems, helping them map the structure of gas clouds surrounding the black hole. These observations provide some of the most detailed insights yet into the inner workings of quasars. Although quasars were first discovered more than 60 years ago, they remain one of the most exciting areas of research in astronomy. Each new telescope, each new observation, and each new discovery reveals more about these extraordinary objects. They are not only the brightest objects in the universe, but also among the most powerful laboratories for studying extreme physics. Through the study of quasars, scientists are exploring how black holes grow, how galaxies evolve, and how the universe itself has changed over billions of years. And as we continue to look deeper into space, the light from these distant cosmic beacons will keep guiding our understanding of the vast and mysterious universe we inhabit. One of the most fascinating aspects of quasars is the extraordinary environments that exist near the supermassive black holes that power them. These environments represent some of the most extreme conditions found anywhere in the universe. Gravity, radiation, and magnetic fields combine in ways that push the laws of physics to their limits. At the center of every quasar lies a supermassive black hole surrounded by an accretion disk of intensely hot gas. As material spirals inward, it accelerates to enormous speeds. In the inner regions of the disk, gas can move at a significant fraction of the speed of light. This rapid motion produces enormous friction and turbulence. Temperatures within the inner disk become so extreme that atoms are stripped of their electrons, forming plasma. This plasma emits powerful radiation across the electromagnetic spectrum, including ultraviolet light and X-rays. The radiation produced by this region is so intense that it can influence matter far beyond the immediate surroundings of the black hole. But the extreme conditions do not stop there. Close to the event horizon, the boundary beyond which nothing can escape, the effects of Einstein's theory of relativity become incredibly important. Time itself begins to behave differently. For an observer far away from the black hole, time appears to slow down for objects moving close to the event horizon. This effect is known as gravitational time dilation. If a spacecraft were somehow able to approach the edge of a supermassive black hole, time for the astronauts on board would pass more slowly compared with observers far away. Although such journeys remain purely hypothetical, these relativistic effects are real and measurable. Astronomers studying the light from quasars can observe shifts and distortions in the radiation emitted by gas orbiting near black holes. These distortions provide important clues about the intense gravitational environment near the quasar's central engine. Another remarkable phenomenon occurring in quasars is the formation of powerful winds. As the accretion disk radiates enormous amounts of energy, some of that radiation pushes outward against the surrounding gas. This pressure can accelerate large quantities of material away from the black hole at extremely high speeds. These winds can travel thousands of kilometers per second. In some cases, they carry enough energy to affect the entire host galaxy. Astronomers have observed quasars ejecting huge streams of gas that extend thousands of light-years away from the galaxy's core. These outflows may play a crucial role in shaping the evolution of galaxies. If too much gas accumulates in a galaxy's central regions, star formation could continue indefinitely. But quasar-driven winds may remove or heat that gas, preventing it from collapsing into new stars. This process helps regulate the growth of galaxies and may explain why some galaxies stop forming stars after a certain point in their evolution. The interaction between quasars and their host galaxies represents a major area of research in modern astronomy. Another striking feature of quasars is the enormous relativistic jets that many of them produce. These jets are narrow streams of particles, traveling at speeds very close to the speed of light. They emerge from regions extremely close to the black hole and extend far into space. The exact mechanism that launches these jets is still being studied, but magnetic fields appear to play a central role. As the accretion disk rotates around the black hole, it drags magnetic field lines along with it. These twisted magnetic fields can accelerate charged particles and direct them into narrow beams shooting outward from the poles of the black hole. Some of these jets extend millions of light-years into intergalactic space. When the jets collide with surrounding gas, they produce shock waves and powerful radio emissions. These emissions are often detected by large radio telescopes on Earth. In some cases, the jets from quasars can even influence the formation of nearby galaxies by heating the surrounding gas and preventing it from cooling. Thus, quasars can shape the structure of entire galaxy clusters. The study of these jets has provided valuable insights into the physics of high-energy particles and magnetic fields in extreme environments. Another fascinating aspect of quasars involves the incredible distances at which they can be observed. Some of the most distant quasars known today are located more than 13 billion light-years away. This means that the light we see from these objects began its journey when the universe was only a few 100 million years old. Detecting such distant quasars allows astronomers to study the earliest periods of cosmic history. In recent years, powerful telescopes have discovered quasars that formed during the first billion years after the Big Bang. These discoveries are incredibly important because they provide evidence that supermassive black holes already existed during the earliest stages of galaxy formation. Understanding how these enormous black holes formed so quickly remains one of the biggest challenges in astrophysics. Another remarkable property of quasars is their variability. Unlike stars, which shine with relatively steady brightness, quasars can change their luminosity over relatively short periods of time. These changes occur because the flow of gas within the accretion disk is constantly evolving. When gas clouds collide or spiral closer to the black hole, the disk may temporarily release more energy, causing the quasar to brighten. At other times, the brightness may decrease as the supply of gas changes. By monitoring these variations, astronomers can estimate the size of the quasar's central region. Because light cannot travel faster than a certain speed, rapid fluctuations in brightness must originate from a relatively small area. This method has confirmed that the extremely bright regions producing quasar radiation are surprisingly compact. Despite emitting energy comparable to entire galaxies, the central engine of a quasar may occupy a region only a few light days across. This extraordinary concentration of energy further supports the idea that supermassive black holes are responsible for powering quasars. Quasars also help astronomers understand the large-scale structure of the universe. Because their light travels across vast distances, it passes through enormous regions of intergalactic space before reaching Earth. Along the way, the light interacts with clouds of gas that exist between galaxies. These gas clouds absorb certain wavelengths of light, leaving distinctive patterns in the quasar's spectrum. By analyzing these patterns, scientists can map the distribution of matter across the universe. This technique has revealed the presence of vast filaments of gas and dark matter, forming the cosmic web that connects galaxies across immense distances. Without quasars acting as bright background sources, these delicate structures would be extremely difficult to detect. Even after decades of study, quasars continue to reveal new insights about the universe. They represent a unique intersection of many different areas of astrophysics, from black hole physics and galaxy formation to cosmology and the large-scale structure of the universe. Each new observation brings scientists closer to understanding how these extraordinary objects form and evolve. Quasars remind us that the universe is far more dynamic and powerful than the quiet night sky might suggest. Hidden among the distant galaxies are engines of unimaginable energy. Supermassive black holes feeding on vast clouds of matter and shining across billions of light years of space. And as our telescopes continue to grow more powerful, the light from these distant cosmic beacons will continue to illuminate the mysteries of the universe. As technology has improved, astronomers have developed increasingly powerful tools to study quasars in greater detail. Modern telescopes are capable of observing these objects across many different wavelengths of light, from radio waves to gamma rays. Each part of the electromagnetic spectrum reveals a different aspect of the extreme environment surrounding a quasar. Radio telescopes, for example, allow scientists to observe the enormous jets that many quasars produce. These jets can stretch for hundreds of thousands or even millions of light years through space. When the jets interact with surrounding gas, they produce strong radio emissions that can be detected by arrays of radio antennas on Earth. One of the most important radio observatories in the world is the Atacama Large Millimeter Array, located high in the Chilean Andes. This facility consists of dozens of antennas working together as a single giant telescope. By combining signals from multiple antennas, astronomers can achieve extremely high resolution and study distant quasars with remarkable precision. Radio observations have revealed that quasar jets are not smooth streams of particles, but highly structured flows containing knots, shocks, and regions of intense magnetic activity. These features provide clues about how energy is transported from the black hole to the outer regions of the galaxy. In addition to radio waves, quasars emit powerful radiation in the X-ray portion of the spectrum. X-ray telescopes, such as the Chandra X-ray Observatory and XMM Newton, allow astronomers to study the hottest regions of the accretion disk. The inner parts of the disk are heated to such extreme temperatures that they emit large amounts of high-energy radiation. By analyzing this radiation, scientists can learn about the behavior of matter under intense gravitational forces. X-ray observations also reveal the presence of highly ionized gas moving at enormous speeds near the black hole. These gas flows provide evidence for the powerful winds produced by quasar accretion disks. Another important window into the quasar environment comes from infrared observations. Much of the dust surrounding the central regions of a quasar absorbs ultraviolet radiation from the accretion disk and re-emits it as infrared light. Observing this infrared radiation allows astronomers to study the dusty torus that surrounds the black hole. The James Webb Space Telescope, launched in 2021, is especially well suited for this type of research. Webb's infrared instruments allow scientists to observe quasars that formed during the earliest periods of cosmic history. Because the expansion of the universe stretches light toward longer wavelengths, extremely distant quasars appear primarily in infrared light when observed from Earth. Webb's sensitivity makes it possible to detect these ancient objects and study them in detail. In recent years, observations from Webb have already revealed quasars that existed when the universe was only a few 100 million years old. These discoveries have surprised astronomers because they suggest that supermassive black holes formed much earlier than previously expected. Understanding how these early black holes grew so rapidly remains one of the most important challenges in modern astrophysics. Another powerful technique for studying quasars involves the use of spectroscopy. When light from a quasar is spread out into its component wavelengths, it produces a spectrum containing detailed information about the object's composition, temperature, and motion. The spectral lines observed in quasars are often extremely broad due to the high velocities of gas orbiting near the black hole. By measuring these lines, astronomers can determine how fast the gas is moving and estimate the mass of the black hole driving the quasar. Spectroscopy also allows scientists to detect the absorption signatures of gas clouds located between Earth and the quasar. As the quasar's light travels through intergalactic space, it passes through numerous clouds of hydrogen gas. Each cloud absorbs a specific wavelength of light, producing a series of dark lines in the quasar's spectrum. This pattern of absorption lines is known as the Lyman alpha forest. The Lyman alpha forest provides a powerful tool for mapping the distribution of hydrogen gas across the universe. By studying the spacing and strength of these absorption lines, astronomers can learn about the structure of the intergalactic medium. These observations have helped reveal the existence of the vast cosmic web, a network of filaments composed of gas and dark matter that connects galaxies across immense distances. Another important technique for studying quasars is gravitational lensing. According to Einstein's theory of general relativity, massive objects can bend the path of light, traveling near them. When a massive galaxy lies between Earth and a distant quasar, its gravity can distort and magnify the quasar's light. In some cases, the gravitational field of the foreground galaxy can split the quasar's light into multiple images. Astronomers observing these systems may see several identical points of light arranged in arcs or rings around the lensing galaxy. Studying these lens systems allows scientists to measure the distribution of mass in the foreground galaxy, including its dark matter. Gravitational lensing can also magnify distant quasars, making them easier to observe with current telescopes. This technique has allowed astronomers to study some of the most distant quasars ever discovered. Another exciting area of quasar research involves time-domain astronomy. Instead of studying objects as static sources of light, time-domain astronomy focuses on how objects change over time. Quasars are ideal targets for this type of study because their brightness often varies. These variations occur as the flow of gas within the accretion disk changes. By carefully monitoring these fluctuations, astronomers can gain insights into the structure of the disk and the behavior of matter near the black hole. One technique known as reverberation mapping uses these brightness variations to measure the size of the regions surrounding the black hole. When the brightness of the accretion disk changes, nearby gas clouds respond by emitting more or less radiation after a short delay. By measuring this delay, astronomers can estimate the distance between the disk and the gas clouds. This method has become one of the most important ways of studying the inner regions of quasars. Modern surveys of the sky are now discovering thousands of new quasars every year. Projects such as the Sloan Digital Sky Survey have mapped large portions of the sky and identified vast numbers of quasars at different distances. These surveys allow scientists to study how the population of quasars has changed over billions of years. by comparing nearby quasars with those from the early universe. Astronomers can trace the growth of supermassive black holes and the evolution of galaxies over cosmic time. In the coming years, even more powerful observatories will further transform our understanding of quasars. The Vera C. Rubin Observatory, currently under construction in Chile, will conduct an enormous survey of the entire sky. It will repeatedly image the sky over a 10-year period, allowing astronomers to detect changes in the brightness of millions of objects. This survey is expected to discover vast numbers of variable quasars and provide new insights into how these objects evolve. Future space telescopes and next-generation radio arrays will also allow scientists to probe the environments around supermassive black holes with unprecedented detail. As these instruments come online, they will help answer some of the most important questions about quasars: how they form, how they grow, and how they influence the galaxies around them. Although quasars appear as tiny points of light in telescopes, they represent some of the most powerful and complex systems in the universe. Through the combined efforts of modern astronomy and advanced technology, scientists are gradually uncovering the secrets of these extraordinary cosmic engines. And with every new discovery, quasars continue to illuminate not only the distant reaches of space, but also the deeper history of the universe itself. Although quasars are among the most powerful objects in the universe, they do not last forever. The brilliant phase that defines a quasar is only one chapter in the life of a galaxy's central black hole. Over time, the activity that fuels these cosmic beacons gradually fades as the supply of gas feeding the black hole begins to disappear. To understand how quasars evolve, astronomers study the long-term relationship between supermassive black holes and the galaxies that surround them. At the heart of nearly every large galaxy lies a supermassive black hole. These black holes can range in size from millions to billions of times the mass of the Sun. In most galaxies today, including our own Milky Way, these black holes are relatively quiet. They sit at the center of their galaxies without producing the enormous energy associated with quasars. But in the past, many of these black holes were likely far more active. During periods when large amounts of gas fall toward the black hole, the accretion disk forms and begins producing enormous radiation. The galaxy enters an active phase, becoming what astronomers call an active galactic nucleus, or AGN. Quasars represent the most luminous and energetic form of these active galactic nuclei. However, the active phase cannot continue indefinitely. The accretion disk requires a steady supply of gas to maintain its brightness. If that supply is interrupted or exhausted, the disk begins to cool and fade. Eventually, the quasar shuts down. The black hole remains, but the powerful radiation that once illuminated the galaxy disappears. Astronomers believe that quasar activity may occur in episodes rather than as a single continuous phase. A galaxy might experience several active periods over billions of years. Each time new gas flows into the central region, perhaps triggered by a galaxy collision or the movement of gas clouds within the galaxy, the black hole may become active again. During these periods, the galaxy briefly shines as a quasar before eventually returning to a quieter state. Evidence for these cycles has been found in observations of galaxies showing signs of past quasar activity. Some galaxies contain enormous bubbles or cavities in their surrounding gas that appear to have been carved out by powerful jets from an earlier active phase. These structures suggest that the central black hole once released enormous energy, before eventually becoming dormant again. Another interesting phenomenon associated with quasars is known as quasar feedback. When a quasar becomes extremely bright, the radiation and winds produced by its accretion disk can dramatically affect the galaxy around it. These powerful outflows may sweep large amounts of gas away from the galaxy's central regions. This process can have profound consequences for the galaxy's future. Gas is the raw material from which stars are formed. If quasar winds remove or heat this gas, the formation of new stars may slow down or even stop entirely. Astronomers believe this mechanism may explain why some massive galaxies appear to stop forming stars after reaching a certain stage in their evolution. Instead of continuing to grow indefinitely, these galaxies become dominated by older stars while new star formation declines. In this way, quasars may act as a natural regulator for galaxy growth. The relationship between black holes and their host galaxies has become one of the most important discoveries in modern astrophysics. Observations have revealed a remarkable correlation between the mass of a galaxy's central black hole and the size of the galaxy's central bulge of stars. This relationship suggests that the growth of galaxies and the growth of their black holes are closely connected. Although the exact mechanisms behind this connection are still being studied, quasar feedback is believed to play a major role. Another area of active research involves the lifetimes of quasars. Scientists estimate that a typical quasar phase may last between 10 million and 100 million years. While this may seem like a very long time, it is relatively short compared with the billions of years over which galaxies evolve. This short lifetime helps explain why quasars are relatively rare in the nearby universe today. Most galaxies have already passed through their most active phases. However, by observing the quasars at different distances, astronomers can reconstruct how the population of these objects changed over cosmic history. These studies show that quasar activity peaked roughly 10 billion years ago, during a period when galaxies were still rapidly forming and merging with one another. During that time, enormous amounts of gas were available to feed supermassive black holes. As the universe aged and galaxies matured, the available fuel gradually diminished, causing the number of active quasars to decline. Even though most quasars have faded, their influence may still be visible today. Many of the massive galaxies we observe in the modern universe likely experienced powerful quasar phases in their past. The energy released during those phases may have helped shape the structure of the galaxies we see today. Some researchers even believe that the quasar phase played a crucial role in determining the final size and composition of many galaxies. Another intriguing possibility is that our own galaxy may one day experience a new period of activity. The Milky Way currently contains a relatively quiet, supermassive black hole known as Sagittarius, a star. Although this black hole occasionally consumes small amounts of gas, it does not currently produce the powerful radiation associated with quasars. However, this situation may not remain permanent. In approximately 4 billion years, the Milky Way is expected to collide with the nearby Andromeda galaxy. When these two galaxies merge, enormous gravitational forces will disrupt the motion of gas throughout both systems. Large amounts of gas may be driven toward the centers of the merging galaxies. This influx of material could feed the central black holes, potentially triggering a new phase of intense activity. If that happens, the combined galaxy formed by the merger may briefly host a bright, active nucleus, similar to a quasar. From the perspective of any observers living within the galaxy at that time, the night sky might appear dramatically different. Of course, such events unfold over millions of years, far beyond the timescale of human civilizations. Yet the possibility illustrates how dynamic and evolving galaxies truly are. Quasars are not permanent fixtures in the universe. They represent powerful but temporary stages in the life cycles of galaxies. By studying these extraordinary objects, astronomers can learn how galaxies grow, how black holes evolve, and how the universe has changed over billions of years. Each quasar observed today offers a glimpse into a distant past, when galaxies were younger, more chaotic, and far more energetic than they are today. These brilliant cosmic lighthouses continue to illuminate the story of the universe, revealing how gravity, matter, and energy combined to shape the vast cosmic structures we observe across the heavens. And even as many quasars fade into silence, their light continues traveling across space, carrying with it the history of the universe itself. As astronomers look deeper into the universe, quasars continue to reveal just how extreme and dynamic the cosmos can be. These extraordinary objects represent some of the most powerful engines ever discovered, powered by supermassive black holes consuming enormous amounts of matter. Yet despite everything scientists have learned over the past several decades, quasars still hold many unanswered mysteries. At their core, quasars represent one of the most fascinating paradoxes in astronomy. Black holes are often imagined as objects that simply swallow everything around them. Nothing that crosses the event horizon can escape, not even light. In that sense, black holes appear to be the darkest objects in the universe. But when surrounded by large amounts of gas and dust, black holes can actually become the brightest objects in the entire cosmos. The energy released as matter spirals toward a black hole is so immense that it can outshine the billions of stars in the galaxy surrounding it. This remarkable transformation from darkness to brilliance is what makes quasars so extraordinary. They show that even the most destructive forces in the universe can produce astonishing amounts of light and energy. Over the years, the study of quasars has transformed our understanding of the universe in several important ways. First, quasars revealed that supermassive black holes exist at the centers of galaxies. Before their discovery, astronomers had no clear evidence that such enormous black holes were common in the universe. Today, we know that nearly every large galaxy contains one. Second, quasars provided powerful evidence about the early universe. Because many quasars are extremely distant, observing them allows astronomers to study the cosmos as it appeared billions of years ago. Some quasars formed when the universe was less than 1 billion years old. These objects provide valuable clues about how the first galaxies and black holes formed. Third, quasars have helped scientists understand the complex relationship between black holes and galaxy evolution. The energy released by quasars can influence the gas within their host galaxies, affecting the formation of stars and the overall structure of the galaxy. This discovery revealed that black holes are not just passive objects sitting at the centers of galaxies. Instead, they may play a major role in shaping the growth and evolution of entire galaxies. In recent years, new telescopes have begun pushing the limits of how far we can observe into the universe. The James Webb Space Telescope has already discovered galaxies and quasars that formed much earlier than astronomers expected. These discoveries suggest that supermassive black holes may have formed surprisingly quickly after the Big Bang. Understanding how such massive black holes formed so early remains one of the biggest challenges in astrophysics. Future telescopes may help answer this question. The next generation of observatories, including extremely large ground-based telescopes and advanced space missions, will allow scientists to observe the environments around distant quasars with unprecedented detail. These instruments may reveal how the earliest black holes grew and how they interacted with the galaxies forming around them. Another promising field of research involves studying the gravitational waves produced when supermassive black holes merge. When galaxies collide, their central black holes may eventually spiral together and combine into a single larger black hole. These cosmic mergers produce ripples in space-time, known as gravitational waves. Detecting gravitational waves from supermassive black hole mergers could provide valuable information about the growth of quasars and the evolution of galaxies. New space missions planned for the coming decades aim to detect these signals. Meanwhile, astronomers continue searching for the most distant quasars ever discovered. Each new quasar detected at extreme distances pushes our understanding of cosmic history further back in time. Some of these objects may reveal how the very first black holes formed in the young universe. Others may help scientists understand how galaxies assembled into the vast structures we see today. Quasars also remind us that the universe is far more energetic and dynamic than it might appear from the calm night sky above Earth. Hidden among the distant galaxies are engines capable of releasing unimaginable amounts of energy. Jets traveling at nearly the speed of light, winds powerful enough to reshape entire galaxies, and disks of glowing plasma swirling around black holes. All of these phenomena occur within the environments surrounding quasars. Yet from our vantage point on Earth, these immense cosmic events appear as tiny points of light. The light from many quasars has traveled billions of years before reaching our telescopes. During that journey, the universe itself has expanded. Galaxies have formed and evolved, and countless stars have been born and died. In this sense, every quasar is a messenger from the distant past. Its light carries information about the universe at the moment it was emitted, allowing astronomers to study cosmic history in ways that would otherwise be impossible. The study of quasars continues to push the boundaries of human knowledge. Each observation reveals new details about black holes, galaxy formation, and the structure of the universe itself. And with every new discovery, scientists are reminded that even the brightest objects in the cosmos began as mysteries. Quasars once appeared as strange radio signals from distant points in the sky. Today, They are understood as the blazing centers of galaxies powered by supermassive black holes. Yet even now, they continue to challenge our understanding of physics and cosmology. As future generations of telescopes peer deeper into space, quasars will remain among the most important guides for exploring the universe. They are cosmic beacons shining across billions of light years, revealing the violent processes that shaped the early universe and continue to influence galaxies even today. And perhaps most remarkably, they remind us that the darkest objects in existence can sometimes produce the brightest light the universe has ever seen.